Section 9.4 Hypothesis testing for the proportion of a population. There are situations where we are interested in testing the claim about the population proportion rather than the mean. For example, we might perform a hypothesis test to determine the proportion of citizens who intend to vote for the Democratic candidate in an upcoming election. We learned that we can calculate the sample proportion or p-bar using equation 9.3. P-bar is equal to x divided by n, where x equal the number of observations of interest in the sample, or successes. N is equal the number of size. The test statistic is found using equation 9.4. Z of p equal to p bar minus p of null hypothesis divided by square root of p null hypothesis times 1 minus p null hypothesis divided by n, where Z of p equal to the z-test statistic for the proportion. P bar equal the sample proportion. P of null hypothesis is equal the population proportion, which is assumed to be true in the null hypothesis. N is the sample size. An example of a one-tailed hypothesis test for the proportion. In January 2011, the French government passed legislation requiring that at least 40% of corporate board members of large companies to be female within 6 years. Large companies are defined as those having more than 500 employees or revenue over 5 million euros. A survey performed by Corporate Women Director International in 2013 found that 25% of corporate board members in large French companies were women, compared to 21% in the US. Suppose the French government would like to test the hypothesis that the proportion of female board members is currently more than the reported 25% in 2013 due to the current legislation. Out of a random sample of 240 French board members, 73 were found to be women. We will test this hypothesis with alpha equal to 5%. Hypothesis tests for the proportion follow the same 6 steps discussed earlier in the chapter. Step 1. Identify the null and alternative hypothesis. Null hypothesis P less than or equal to 25% or status quo. Null hypothesis, alternative hypothesis P greater than 25%. Step 2. Set a value for the significant level alpha. We will use alpha equal to 5%. Step 3. Determine the appropriate critical value. Because proportion data tend to follow the binomial distribution, which we can approximate with the normal distribution, we can use table 9.5 to determine the critical z-score. A one-tailed test which alternative hypothesis P greater than 25% and alpha equal to 5% result in z alpha equal to 1.645. Step 4. Calculate the appropriate test statistic. Use equation 9.3 to find our test statistic, where p bar equal to x divided by n equal to 73 divided by 240 40 equal to 30%, 30%. Z proportion equal to P bar minus P of null hypothesis divided by square root of P null hypothesis times 1 minus P null hypothesis divided by N. This equal to 0.305 minus 0.25 divided by square root of 25 times 1 minus 25 divided by 240 equal to 1.94. Step 5. Compare the test statistic or Tx bar with critical t-score or T alpha. Since the Z proportion equal to 1.645 and Z alpha equal to 1.94, and because 1.94 is greater than 1.645, we reject null hypothesis. Figure 9.15 illustrates this finding. Step 6. State your conclusion. Rejecting the null hypothesis indicates that we have support for the alternative hypothesis. Alternative hypothesis is P greater than 25%. Therefore, we can conclude that the proportion of female board members in France has increased beyond 25%. The p-value approach to hypothesis testing for the proportion. The p-value approach for the hypothesis test for proportion is identical to the procedure for the mean when the population standard deviation is known. For French board example, a one-tailed test, the p-value is the probability of obtaining a sample proportion higher than 0.304 if the true proportion is 0.25. Therefore, the p-value is as follows. P of p bar greater than 0.304 equal to P Z of proportion greater than 1.94 equal to 1 minus 0.9738 equal to 0.0262. This p-value is represented by the shaded area in the right tail of the sampling distribution shown in figure 9.16. Because the p-value equal to 0.0262, which is less than alpha equal to 0.05, then we reject the null hypothesis.